We are going to do some notes. We're going to do some good, fun, heavy-duty algebra. This is like stretching before practice. This is good. We're going to stretch the algebra muscle. You already saw constant acceleration. In your lab, you saw, and a few people had really gorgeous data, that as an object accelerates, the distance it travels in each interval gets bigger. And as long as the rate of acceleration is constant, this makes possible a whole host of other things. So what we're going to do is take the two base equations that we've got so far, and we're going to rearrange them into what I call the four golden equations. Those are going to be the foundation of everything else you do, pretty much up through the next two chapters. I have had people threaten to get the four golden equations tattooed on their forearm. I think it's a fine idea. I haven't done it myself, but, you know, oh well. All right, so we're going to start off. We're going to start off here, finding displacement with a constant uniform acceleration. And though you've got the derivation on the slide, I think it actually makes more sense if we do it step by step together. Reading it on the slide isn't the best way to do it. So remember that we're starting off with only two equations, and right now, all we're using is V average equals delta x over delta t. One bit of feedback that I've gotten from former students, because I make you derive all the stuff by hand from scratch repeatedly, because I'm evil. No, because it makes more sense that way. So there are all these shortcuts. You know, we use this derivation in this circumstance, use this derivation in this circumstance, and what ends up happening is you can't always keep track which circumstance is which circumstance. So I'm a big believer in deriving it yourself every time because you know what factors are on the table and what factors aren't. So it actually, again, is useful brain calisthenics. All right, so we've got average velocity is equal to the change in position over the change in time. And I know that if my acceleration is completely constant, then average velocity is also equal to VI plus VF divided by 2. That's a useful one. I have sometimes actually put this on a note card. There are a few instances where remembering that comes in handy. I would say that this particular little thing comes in handy on the lab that you're going to start later next week. You might or might not want to, you know, make a star by it. So we can sub some things in, and then we can say that VI plus VF divided by 2 is equal to delta x over delta t. Okay. If we want to rearrange and solve for displacement, then we can say, well, 1/2 VI plus VF times delta t gives us delta x. And usually just as a matter of form, I write the thing solved for on this side. So on my note card, it looks like this, 1/2 VI plus VF delta t. And that is actually the first of your four golden equations right there. Delta x equals 1/2 VI plus VF delta t. Okay, so that gets us to the 2C problems. We'll do the sample problem together, and then I'll assign the 2C practice problems. Okay, so we say that a race car reaches a speed of 42 meters per second, then begins a uniform negative acceleration using the parachutes and braking system and comes to rest 5.5 seconds later. How far does the car move while stopping? So we're going to write down our equation, and in this case we're going to use delta x equals 1/2 VI plus VF delta t. I'm going to list my variables, VI, VF, delta t, and I'm listing delta x, but I'm putting a question mark by it as a reminder that that's the thing I'm looking for. So VI is 42 meters per second. They gave you 2 sig figs to work with. What's VF? Is it given in the problem? It stopped. What's its VF? 0. 0 meters per second. And it says that it comes to rest 5.5 seconds later. That from rest, we'll often see problems where it says something starts from rest or comes to rest. That gives you an either VI or VF. That at rest is for 0. So this is great. We don't even have to do any rearrangement. Delta x equals 1/2 42 meters per second plus 0 meters per second times 5.5 seconds. Give a delta x of 115.5 meters. Let's do a quick dimensional analysis check. Meters per second plus meters per second is meters per second times seconds. And I'm going to say that my 5 and my s are not the best drawing I've ever done in my life. There, that's better. So we do get meters. How many sig figs can we have? 2. 2 sig figs, because both of these have 2 sig figs. So delta x would be 120 meters. Okay. Assigned are all of the 2C problems on page 53. So 2C, page 53, all. I'm going to give you about 15 minutes to start on those, and then we'll move on to the 2D and 2E problems. So grab a book. When you're faced with it, now right now it's really easy because we've only dealt with 3 equations. We only have 3 equations to pick from, and we've kind of been going in order, one at a time. But that won't always be the case. So while I've been saying, write down your equation, list your variables, really I should flip that. And the first thing you have to do is write down your variables. Because as the problems get more complex, writing down your variables tells you which equation to use. Because the variables that you have in the problem guide your choice. That's the whole secret to physics. And it's very easy if you allow that process to happen. So, that said, let's go on to deriving our next 2 goldens. All right, this is a slightly uglier derivation, and I always run through these before I try to do them cold, and this one took me 2 little scraps of paper. So it's a little bit longer. Give yourself some space for it. So if we don't know what VF is, but we know VI, we know delta t, and we have constant acceleration, then we can start off, and I'm going to shrink this, hold on, with A equals delta V over delta t. And we know that delta V is just VF minus VI. So we have that. And we can actually, interestingly enough, solve for VF using this. So we have A delta t equals VF minus VI. A delta t plus VI equals VF, except I usually write it like this, VF equals VI plus A delta t, and the reason being that it's totally logical to me, and maybe to you too, if I look at it and say, oh, well, your final velocity is your initial plus your rate of acceleration and how long you've had to accelerate. So it's one of the golden equations that when you read it in that order, just seems like common sense. So VF equals VI plus A delta t, and that's the second of your golden equations. So I would put that on your note card. VF equals VI plus A delta t. Your final velocity is your initial plus your rate of acceleration, how long you have had to accelerate. This is one of the slightly hairier bits of derivation. So if we remember that we have this, which of course you remember, we just did it. Note that this is all equal to VI. Now, we already said that delta x equals 1/2 VI plus VF delta t. Okay. Well, we have this VF here, which means we can plug that whole mess into there. And we do this a lot. This is a substitution and solve. When we get to chapter 3, we do pretty much nothing but substitution and solves, and that's the only way to solve 2-dimensional motion problems. So now we have to hang on tight for the algebra, VI plus, and I usually use both brackets and parentheses just to keep myself sort of halfway straight. And I'm going to distribute the 1/2, and I'm going to distribute the delta t. So what we'll end up with is delta x equals 1/2 VI delta t plus 1/2, whoops, 1/2 VI plus 1/2 A delta t squared. Okay, so, delta t. There we go. Well, geez Louise, I made that about as messy as I possibly could. Let me move that over a little bit. 1/2 VI delta t. So I can combine like terms. 1/2 VI delta t plus 1/2 VI delta t, let me shrink this, gives me VI delta t, and then I have plus 1/2 A delta t squared. So the displacement is equal to the initial velocity times time plus 1/2 the acceleration times time squared, which doesn't seem intuitive in any way, shape, or form. But it's a really useful equation. So this is the second, or the third rather, of your golden equations. Delta x equals VI delta t plus 1/2 A delta t squared. So we have a plane starting at rest at one end of the runway undergoing uniform acceleration. We're given the uniform rate of acceleration for 15 seconds before takeoff. What's its speed at takeoff? Well, we have VI. We have A, we have delta t, and we're looking for VF. VI is what? 0. Acceleration is 4.8 meters per second squared. Delta t is 15 seconds, and we'd like to know VF. Again, we now are up to 3 of the golden equations, plus our little simpletons at the beginning. So we want to use the variables we have to guide our choice of equation. So we have VIA, delta t, and VF. Is there any equation we have that links those 4 things? Yeah, we just talked about it. VI, whoops, geez Louise Moser. VF equals VI plus A delta t. Your final velocity is equal to your initial plus your rate of acceleration times how long you've had to accelerate. Okay, plug it in. If we do a little bit of dimensional analysis, meters per second squared times seconds would give us meters per second. Raw answer is 72 meters per second. Sig figs are already correct, so we're good. Now they ask, how long does the runway have to be if the plane's going to take off successfully? So now we're looking for delta x. And I'm going to give you a word of caution. And this is a very, very serious word of caution. You just calculated the final velocity of the plane. Could you plug that in to your next equation? You could. And it might be just fine. But if you made any error in calculation in the first part, you've then just shot yourself in the foot for the second part. So whenever possible, go back to the givens. Don't use numbers you have calculated unless there is no other way around it. And believe me, I have done some wildly torturous paths to get around using a number that I've calculated. Substitution is better because you're doing it all at one shot and it enables you to do other things. But if you can help it, don't use numbers you've calculated as a given. Go back to your original givens. Let me pause. So if I want to solve for the length of the runway without using VF, I have VIA, delta t, delta x. Do I have anything that would allow me to solve for that without using VF? Well, of course I do. It's the one that we just derived. So delta x equals VI delta t plus 1/2 A delta t squared. So delta x equals 0 delta t, or oops, 0. Here's the other nice thing, and I usually do this in the first step. As long as VI is 0, that second delta t goes away. So that's how we avoid the quadratic very often. In anything where VI is 0, that first term disappears. So now I have 1/2. Well, our acceleration was 4.8 meters per second, and our time was 15 seconds. Don't forget to square that. That's the most common mistake people, including myself, make on these. We get a delta x of 540 meters. Again, amazingly enough, the sig figs are already correct. So we have a delta x of 540. Assigned are 1 through 4 on 2D. Okay, so assigned 2D, page 55, numbers 1 through 4, and I'll give you some time to get going. What if we don't have time? Ha 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 ha! Who has time? Well, apparently not the person solving this problem. So if we start off with delta x equals 1/2 VI plus VF delta t. I actually like the derivation on this one because I like, what do they call it, difference of squares. Anyway, and we get rid of that half. We multiply everything by 2. So we get 2 delta x equals vi plus vf times delta t. Okay. And we go back and remember that vf equals vi plus a delta t. Well, I forgot to solve. We're sort of doing two parallel things here. So I have 2, let me keep my colors straight, 2 delta x divided by vi plus vf equals delta t. Well, that means, of course, that I have something here solved for delta t, and I have a delta t here into which I can jam that whole thing sideways. Doesn't that look like a whole lot of algebraic fun? Yay! So I'm going to shrink part of this, and I now have this, with this expression for delta t shoved into that. Okay? So I'm going to distribute the a to start with. So vf equals vi plus a 2a delta x over vi plus vf. I'll pause and move. Okay, so I clearly need to simplify this, and the easiest path to doing that is vf minus vi equals 2a delta x over vi plus vf. Well, that allows me to do something. Difference of squares? I can't remember the name. vf minus vi times quantity vi plus vf equals 2a delta x. And if we do the FOIL method on those, does anybody want me to do the FOIL method? Normally I would skip that step. Are you good with that? Okay. Skipping the FOIL on that, what we get out of that is vf squared minus vi squared equals 2a delta x. And this is most commonly written, oh, I missed the little bar on the f again. There. This is most commonly written in the final analysis as vf squared equals vi plus 2a delta x. And that's the fourth of your 4 goldens. Okay. Vi squared. Geez Louise, Moser. Sorry. That would be bad. So this is most commonly seen as vf squared equals vi squared plus 2a delta x. Useful if you don't have time, but you have displacement. You've got at least one of the velocities, and you have the rate of acceleration. Okay, that leads us, of course, to the 2E practice. Okay, so person pushing a stroller starts from rest, uniformly accelerating at a rate of 0.500 meters per second squared. What is the velocity of the stroller after it has traveled 4.75 meters? And again, I'm going to list variables as a first step. Even though we know perfectly good and well what equation they want us to use, because it's 2E and it's all about that one equation, when we start doing mixed practice where you've got things that could be using any one of the 4 goldens, it's really helpful to know which one to pick. So VI, we're given, VI is 0 because it started from rest. Uniformly accelerates. We have a rate of acceleration, 0.500 meters per second squared. And we have a distance, delta x equals 4.75 meters. We have no idea how long this takes. That's the whole point, is we're doing this without having a time interval for it. So what we want is VF. And pretty simple. VF squared equals VI squared plus 2a delta x. We don't really have to rearrange, but we do have to take a square root, and that's simple enough. Let me move this out of the way. So VF is equal to the square root of VI squared plus 2a delta x. I'm going to plug in square root of, 0 squared, well that's still 0, times 2 plus 2 times 0.55500 meters per second squared. I'm going to have to shrink this or move it, or both. Times 4.75 meters. So let's see what we get as our raw answer. First we get 4.75 because it's half a meter per second squared acceleration. So the square root of 4.75, we get a final velocity of 2.179449472 meters per second. And if we look at that, of course, we had meters squared over seconds squared. Square root of that is meters per second. And we have 3 sig figs. So we can actually say that this is a final velocity of 2.18 meters per second. We can say that it's in a positive direction. When there's no sign, it's kind of assumed that we're saying positive. Your book specifies that it is a positive direction because they want to talk about the coordinate system. So we'll keep talking about the coordinate system. I'm not going to stress it on this one. So assigned are 1 through 6 on page 58. These are the 2E problems, and that's it. Go. The big golden note card. Whoa! Like, you know, shafts of light beam down through the clouds, and a chorus sings somewhere in the distance, and kittens come tumbling along, and there are tacos. So, because now Lucas has me thinking about taco night. So this is what should be on your note card along with the 2 basics that we used. We'll add a few things to it as we go, but really these 4 plus the 2 basics will get you all the way through chapter 3. Every single problem we solve, these 4 plus the 2 basics, and we'll talk more about what should and shouldn't go on your note card. Though in the end, it's your note card. All right, keep working.